Hey guys, welcome back to my YouTube channel. Today I'm going to be talking about the synthesis of epoxides and the epoxide ring opening reaction with alkenes. And just to start off, I'm going to be talking about how to make an epoxide. There's two ways to do it. Over here, I have what an epoxide is. It's basically a three-membered ring with an oxygen attached. And you have two ways of doing it. You can use an alkene with a peroxy acid, or you can use a halo hybrid with a strong base. The peroxy acids that are used most commonly are MCPBA and CH3CO3H. And yeah, and for the bases, you can just use any strong base. Most commonly, you'll see KOH. And yeah, that's how you synthesize an epoxide. So I have an example here on the right for synthesizing an epoxide. If we've used molecule from the bottom, right, with stereochemistry, we'll see that this methyl here is on a dash. That methyl's going on a wedge. And so with our peroxy acid, which is MCPBA, we're going to be forming a three-membered ring with the oxygen. And that would be our final product. And this is the trans product. Okay, so after that, we go into the epoxide ring opening. So basically, you're forming your epoxide ring still, but this time you're opening the ring with a weak nucleophile. And so the nucleophile attacks the ring, and in order to do this, the nucleophile needs to also have a bit of acid. And usually the way we do this is we add an acidic hydrogen atom, as we can see here in this example. And yeah, the type of addition that the ring opening is, it can be anti and syn, but I'll explain that later on. It depends on your reagents. You can get the anti-diol or the syn diol, but it really just depends on your reagents, and I actually have them listed down here. If you want the anti-diol, you'll be using your peroxy acid and your acidic hydrogen with the weak nucleophile. And if you want the syn addition, you'd be using cold dilute KMnO4, or you could use OSO4 with your peroxide. But in this first example here, I have the anti-diol reagents. So if we view this molecule from the bottom, with stereochemistry, this molecule would look like this. And those two methyl groups are going to be on a dash. And when we react that with MCPBA, we're going to get an epoxide, right? We have a three-membered ring that's going to form. All right, and in our second step here, we have an acidic hydrogen. It's going to come and attach with this oxygen here. And so our ring will end up looking like this. Okay. And then finally, our weak nucleophile will come and attack our more substituted carbon. So if you see here on the left, this is the more substituted carbon. On the right, we have the less substituted carbon. But anyways, yeah, the water molecule, the weak nucleophile, will come and attack the more substituted carbon. Right, and what this will do is it will open up the ring, and this is we're going to get the anti-diol. And so our final product for this will end up looking something like this. You have OH there and OH there. And that's in the anti-formation. If you think back to Newman projections, you have a dihedral angle of 180 degrees. But let's draw the substitutes on this. This had a methyl group there. And this one had a methyl group coming towards us on a wedge and had an ethyl going away. So this would be your final product for this. And once again, they're in the anti-arrangement. They have a dihedral angle of 180. And what that allows for is the least amount of steric hindrance. Cool. So I have another example here. This example is using a different weak nucleophile. just goes to show that you don't need water as a weak nucleophile for every problem. It can be any weak nucleophile as long as you have an acidic hydrogen as well. So in this example, I'm going to put the methyls on wedges. And MCPBA, our epoxide ring, is going to form like this. And it's going to be the same thing, except this time we're adding the acidic hydrogen. And that acidic hydrogen is going to attach to our ring, our oxygen here, giving a partial positive. Well, not partial positive, but a positive charge. And finally, our weak nucleophile, which in this case is CH3, CH2, OH, it's going to come and attack the more substituted carbon. And both carbons are equally substituted, so we're just going to attack either one. And our final product is going to look something like this. Right, so on the wedge here, I'm actually going to have my weak nucleophile that attacked, and it's going to be deprotonated. So O, CH2, CH3, and my methyl group, those there, I'll just put it on the dash. And the ring that broke, it's going to have the OH on the dash, methyl on the wedge. So the reason I did it like that was because I wanted my final product to be in the anti-arrangement. So if you look here, this OH down here is on a dash, and this right here is on a wedge, right? So that's the anti-arrangement. If they were both on a wedge or if they were both on a dash, then it would be syn. You'd get the syn diol. Okay. All right, so next example, we have OSO4 as our reagent along with peroxide. Whenever you see OSO4 and peroxide or cold dilute KMnO4, this is how you're going to get the syn diol whenever you do your epoxide ring opening. So we can just go ahead and label this. We're going to get the syn diol. And so from this, right, if I'm assuming that's on a wedge over there, we're going to have both of our OHs on a dash this time because it's a syn diol, right? So our final product will end up looking something like this. Right, notice that they're both on a dash. That means we have the syn diol. So that would be our final product for that. You can also get the enantiomer, right? So don't forget that, because if I were to put that methyl group at the start on the dash, then both of our OHs would have been on a wedge. All right, next example. I have cold dilute KMnO4, and once again, this is for your syn diol. And if we look at this molecule from the bottom, I'm going to have this methyl group coming on a dash, coming away from me, or going away from me, sorry. And then methyl right there on a wedge. And our ethyl looks like that. All right, and once we do this, we're going to get the syn diol once again. And so our final product will look something like this. Or hold on, let me actually go through the mechanism here for this one. Right, so our ring is going to form. Right, and then we need to figure out what's our more substituted carbon. On the right, we have the more substituted carbon, more sub, right? So that's where our weak nucleophile will attack, sorry. And so our final product looks something like this, right? We have both of our OHs are on the same side. They're the syn diol. The product is the syn diol. And then we'll have our wedged ethyl there. Wedged methyl. And yeah. Notice how this isn't in the 180-degree anti-formation, right? That's not a dihedral angle of 180. That's because we're using cold dilute KMNO4. So that would be our final product for this question. All right, last question. When I'm looking at this question, I see that I have a peroxy acid. And what our first step is doing is forming the ring. And I'm going to go ahead and draw that here. Oops. I'm going to assume this is on a wedge. You could also assume that it's on a dash. But our ring will form here, right? But then remember, we have the acidic hydrogen atom, and those will give our our oxygen a positive charge. And our weak nucleophile in this example is H2O, right? So our H2O is going to attack the more substituted carbon, and the more substituted carbon is up here. And this is anti-addition, or it's going to be the anti-diol that we're going to get. So our final product, we can draw this ring here. Right, on the wedge, I'm actually going to have my weak nucleophile, that's H2O in this case, and I'm going to deprotonate it. So it's going to be an OH on the wedge. And the methyl that was there before, I'm going to put it on a dash. Okay, and the remembered ring that I broke earlier with the weak nucleophile, it's still going to be on the dash. It's dash OH. And so this would be our final product. If we look at our OH groups, one of them's on a dash, one of them's on a wedge, and so that will be our anti-arrangement. Alright, so things to note for this type of reaction. If you want for the anti-diol, right? So anti-diol means opposite, like it's 180 degrees. It could be wedge and dash, or dash and wedge, same thing. For this, we just use a peroxy acid, right? And we also use an acidic hydrogen atom in our second step, along with a weak nucleophile. For our syn diol, right, we can use cold dilute KMNO4, or we can use OSO4, right? And in our second step of that, H2O2, a peroxide. And yeah, just keep that in mind whenever you're doing these reactions. Pay attention to your reagents so you know what type of stereochemistry you're going to get at the end in your final product. And yeah, aside from that, it's pretty simple. Thanks for watching. See you guys next time. Bye. Thanks.